What's up, everybody? Welcome to Lecture 10 over Section 2.4. Today's lecture is going to be largely just about trig derivatives. And honestly, it's going to be a pretty quick lecture. But to start off with, we have three different primary trig identities. From there, I'm going to leave the other three up to y'all to find and prove on your own. But I'm going to motivate that you can do this and show you how you can do this by proving this identity down here. So to start off with, what I'm going to do is I'm going to break up the derivative of the tangent. What I mean is, I say, all right, well, I know that the tangent of x can be rewritten as sine over cosine. So taking the derivative of the tangent of x is like taking d dx of sine of x over cosine of x. And not just like, it is, right? Because tan x is equal to sine of x over cosine of x. Okay. Well, that's a quotient. That means I'm going to have to use the derivative rule, right? I mean the quotient rule. The derivative rule. The quotient rule is what I need to say. Okay. So I have to use the quotient rule. The quotient rule tells us that d dx of f over g is equal to g times f primed minus f times g primed, all divided by g squared, right? Well, in our case, g is cosine of x, and f is going to be sine of x. So we could rewrite all of this as cosine of x times d dx of sine of x minus sine of x times d dx of cosine of x all divided by cosine squared of x. Okay, now, we know from these two derivatives here what the derivative of sine of x is and what the derivative of cosine of x is. This is going to come out to be cosine of x times, well, that derivative is going to come out to be cosine of x minus sine of x times the derivative of cosine of x. Well, that's negative sine of x all over cosine squared of x. But hey, that means this is going to be cosine squared minus negative sine squared. And minus a negative is the same thing as adding, so this is equal to cosine squared of x plus sine squared of x over cosine squared of x. And hey, we have an identity for this. That numerator It's just a Pythagorean identity, right? So it's going to come out to be 1, because cosine squared plus sine squared is just 1. So this all comes out to be 1 over cosine squared of x. But isn't that the same thing as secant squared of x? And hence, we have just shown that the derivative of tangent of x is equal to the secant squared of x. And it's by knowing these sorts of relationships between sine and cosine that you can find all of the derivative identities for your trig functions. So like I said, I've left off 3. And now that you've seen how to find the derivative of the tangent, you can use that information to figure out how to find the derivative of each of the other trig functions. Having said that, we still got a little bit more to do. So stick around. Well, I don't know why I keep saying stick around. It's only a blip to y'all. I pause it, erase this. It takes more time to me. But to y'all, you don't need to hear me ramble. I'll be right back. Alright, so at this point in the lectures, it's going to help if I introduce a little bit of physics. Bear with me, it's not a whole lot. It's just going to be a very little bit. So, in physics, when we talk about the distance traveled by an object, so how far I just went, right? We oftentimes like to talk about it as a function of time. And we like to denote that function as s, so s of t. And s of t is just a measurement that, with some amount of given time, how far has an object traveled? Okay, that's simple enough. Well, physicists also like to talk about velocity and acceleration. And those things obviously relate to distance traveled. In fact, they don't just relate, they're particular derivatives of the distance traveled. Velocity is the derivative of the distance traveled, and acceleration is the derivative of velocity. Which is really convenient because it means if you want to know any of these bits of information, all you need to know is one of them. So if you were to measure how far an object traveled as a function of time, that's pretty easy. That's something you can visually check, right? Well, from there you have velocity and acceleration. That's nice. That's great actually. That's very convenient. But hey, notice something. This acceleration, we just said, is equal to d dt of v of t, right? So velocity with respect to time. But velocity is a derivative of position with respect to time. So this is actually more like d dt of, let me find another color, so that it's going to be easy to distinguish between. So this derivative is more like ddt of ddt of s of t. Huh. Well, that means you can take more than one derivative of a function? Sure, why not? Yeah, you can take as many derivatives as you want, as long as that function is differentiable. Okay, well, if that's the case, this notation can get really clustered after a while. Because there's also what's called jerk when talking about velocity, acceleration. The next derivative is called jerk. So that would be like d dt of a of t. And after a while, this notation gets really messy. So why don't we condense this down? Why don't we use the convention that for every derivative we apply, we can mark it as a superscript within this notation here. So what I mean to say is, since we are taking two derivatives, why don't we write this as d squared over dt squared? Because what this is saying is you're applying d dt twice, right? So it's like squaring that operator. But, you know, we use other notation too. So this would be traditionally like s prime here, right? But since we're applying two derivatives, why don't we call this s double prime of t? This gives you an idea of how this notation is going to change for higher order derivatives. In fact, after about the third or fourth derivative, usually we just drop this notation entirely, this prime notation. Instead, we'll write, let me erase all of this. Let's say we wanted to take just the general nth derivative. We would write this in the following abbreviated notation. D to the n divided by dt to the n of s of t is equal to s of, and then we'll use a superscript n inside of some parentheses. Now it's important to note, whenever you have a function raised to something inside of parentheses, we're saying that something inside of parentheses is denoting the number of derivatives you have to take. So here it's n number of derivatives, which matches with what we're saying over here, right? We're applying d dt n number of times, which is why we have this particular script that we use here. That said, just to clarify some of this, because it is a little messy to explain without having y'all here in the classroom, I would strongly recommend you check out those notes, because it does a good job of kind of running you through some of this stuff. Having said that, I think that is all I have for y'all today. So, having gone through all of this, feel free to shoot me an email if you have any questions. Otherwise, feel free to go. Have a good one, everybody.